Hi everyone. I am a senior backend engineer at SpaceKnow, and I'm here to talk to you about what challenges do we face and solve when we run Python at planetary scale. So first, what do we do at SpaceKnow? At SpaceKnow, our operations revolve around managing and analyzing petabytes of satellite imagery. And our platform delivers world-class geospatial analysis using our own algorithms that include object detection and classification. These colossal tasks brings along certain challenges unique to these large-scale operations when we analyze huge areas of land or sea all across the globe. Running analysis over whole countries or oceans poses a lot of non-trivial issues, especially if it's needed to be fast. So this talk will expose and address some of these challenges, and will also provide tips and practical examples how to avoid them and how do we keep our sanity while running it. So first, I will give you a short introduction into our platform so you can better understand the problems we are facing. Our research team provides us with machine learning models for various algorithms, and it's our task as a backend team to provide a platform that allows our customers and users to run data analysis over satellite imagery fast and reliably. As this is Python, I'm glad to say that our code base is in Python. Our Python code is running custom Linux Docker images. Pre-built images are running in Kubernetes as many different microservices. Each handles specific task or set of tasks. For people who are not familiar with Kubernetes, our services are wrapped in so-called pods, and you can imagine it as a single instance of a service or single VM instance for simplicity. Our Kubernetes are running in the cloud. As of now, we are mostly using Google Cloud, but our platform is made to be cloud agnostic, so meaning we try to design it so it can run across different clouds, or you can run it on your own hardware if it's needed. However, we are trying to use some tools that Google provides to us, and so I will mention some specific tools that Google is good at. And the main reason we use all that is so we can automatically scale down an app as we need. So to give you an idea what we do, this is an example of one such analysis. It contains segmentation over the urban area. Each color represents different segments: road, urban, non-urban, trees, cars, and so on. Then this is another type of analysis. This is example of object detection. So the goal is to detect different types of aircraft. This is usually done across months or years to see the changes over the airport. Then there's another types of imagery. For normal imagery, you basically are limited to what you can see when the cloud cover is not there. So there is another type of imagery called SAR imagery, meaning synthetic aperture radar, basically radar imagery. And this is an example of what you can see with radar imagery through the clouds. And this is the change. So you have two images, and you try to find out what's changed between those two. So this brings me to the first general problem we are usually solving. How do you analyze huge areas fast? Or fast even across, let's say, years in the past. So what I already said is we scale our compute resources. And to do that, we have to split our tasks into smaller tasks. That is not possible for all your compute workloads. However, for our use case, which is analyzing satellite imagery, that is very doable, even if it's not really trivial. So in this talk, when I refer to parallel processing, I'm referring to workflows running in parallel with parallel tasks. So to make sure that each task finishes eventually, we use directed acyclic graphs. And some of you might remember it from school, and it's very handy for our use case. So what is it? This is the DAG example. D means directed, so that is shown by the arrows. A means acyclic, so means one task don't get stuck in infinite loops. And what is useful for us is actually the second row. So one parent task spawns 4 different tasks or splits, and in theory it could be 4 times as fast if it was done in sequence. So executed tasks are then joined, and you are finished faster than before. So this is the demo example. So what kind of DAGs are we running? Well, on the top is a zoomed out image of one such a DAG over the scene. Each tiny dot is a separate task. And the red square, below it, you can see the zoomed out image. So you can see each of the square is a task. And this graph is analyzing 50 kilometers squared over some country, let's say. And you can be running hundreds of those if you need huge areas. Usually the longest time is spent downloading the imagery from our providers. And once you are split this parallel, it can finish in minutes. So I'll be talking about 4 following topics. So how do we utilize Python logging capabilities to maintain our context and traceability of logs in our distributed system? Then about versioning. So how do you manage our pip and system packages for running Python in Docker? So yeah, that can also be tricky. Then I will talk briefly about parallelism. So the slide you've seen before. And I will talk about resource scaling. So how do we manage our applications and automatically scale Kubernetes from Python? Before I dive in, I just want to make a disclaimer. If I had to give you one advice, if you don't have to, don't use this type of workflows, as running parallel processing can get very complicated very fast, and usually running on single powerful machine is underrated. But for our use case, it is necessity and extremely powerful. So I will start talk about logging. I won't be talking about logging basics. So there are great talks about it somewhere else on the internet, and I will tell you about specific issues with logging, or especially with Python logging, that we experience if you log a lot, especially in the cloud. So what's the goal is find out what's happening right now in our platform, find out what happened in the past, get notified about failures, quickly be able to find a failure, be able to trace the failure to the source that caused it. And our bonus goal is to report statistics of what happened in some aggregated view. So our first problem, how do you log across hundreds of pods at the same time? Users see some weird behavior, complains about it. How can you track what happened? So that request could travel through hundreds of pods until it's successfully completed. One way to solve it is to have each log contain context, what happened and why it happened. And so, for example, you receive request ID from the user. It goes, for example, through Nginx, and Nginx assign it the request ID. We want to keep that. So there are many ways how to do that. For example, since Python 3.7, you can use context vars to keep the context, which acts as a global storage. And anytime you can instruct your logging, So anytime the log is done, it includes request ID in the log message. And I recommend reading to Python logging cookbook to learn more about it, different ways how to save this kind of context. So great, you solved the first issue. The second issue is logs can be hard to search through. So you can do full text run over the request ID, but say you want to search what requests by two specific users. Text search might not be the best for your use case this way. So the great thing is in Python, you can log directly in JSON. And yet, again, the official Python logging cookbook has you covered and contains examples how to log as structured messages. So now, whether you use Google Stack Driver, which is Google logging tool, or, for example, Elasticsearch, you can directly filter on the names of the JSON fields. Meaning I can search for specific user ID and all his requests. Or if I have a failed pipeline, I can search all the way back through the request ID to see what caused it. So you fix that, and now there's another problem. You log everything with JSON, you can search. However, some unexpected error happens on your platform. Sad thing about these kind of unexpected errors is you're not expecting them, so you're not handling them. And if it's not running in the API or it's simply raised, then it's just dumped into standard error output and your program fails. This kind of errors can be incorrectly parsed by your loggers in the cloud. And even worse, when this happens, you lose your context because it's not really logged. Well, the great news is, since Python 3.8, you can actually override except hook, which means that every error that occurs on your platform, you can wrap into the log, and that could include your context. Well, so now you have it working well, and you update your packages, and you see some warnings start to show up. And you find out that warning is not logging warning, and it's not logged by default. So this is luckily has very simple solution, is just you change a single flag and make sure that warnings are properly logged, and you won't lose your context yet again. So, and there's another issue so everything's working great, but one day you log too much. Your logs are taking too much space, or HDD gets full, or even worse, when you're running the cloud, your provider is starting to charge you for storing so much logs. This is normally something that's not noticeable, but at our scale, it can get expensive. So you want to get rid of your logs, but they are very important to you. You pick them for a reason, but you still need to save space and money. So what do? We keep as little of context for info messages because they are pretty much stable, but we are adding as much context possible for warning and error messages. So in the example, we want to include the source location of the error in the code for better tracing, but we don't really need it for info logs. We are aware where these are logged. Which brings me to final logging issue. So your logging works great, but one day your boss asks you to, so how long does this specific task take? How much area did we analyze yesterday between 4 and 5 p.m.? You might write row to your database every time the new area is analyzed. However, that will probably slow down the delivery, and add additional complexity. But if you are logging with enough context, then all the information you need is available in logs. And some of that information can be pretty interesting. So this is Google-specific tip. I'm not sure if some other cloud providers do that. But for example, in Google Cloud, you can pass selected logs directly to BigQuery, which is SQL database. And what we do, for example, we have logs with JSON field type analysis. It contains fields, how much area was analyzed, which user did it, and then we are able to move it directly to SQL database and have reports on top of it, which is great. So you have almost real-time logs in this case, or real-time reports. So that brings me to another issue. What is versioning good for? So we want to guarantee the stability of the platform and have predictable outputs. We want to find out about breaking changes fast and be able to find dependency that cause them. And we want to be as much as up to date to the possible, so our dependency have fixed bugs. So first problem is very basic, and this is nothing new. We are not using anything fancy. We're just using, however, this works pretty great, so we don't need any dependency management. When building our Docker, we just use the simple requirements.txt, which we keep in Git, and we try to have most dependency as much as up to date as possible and unrestricted. So now you have your requirements file, and your requirement file stays the same, but after your update, something breaks. So what happened? Well, probably some of the unrestricted packages changed and broke something. Here we do very basic thing where we just freeze installed packages to Git every time we update our Docker image. And this way we can track the changes and be able to pinpoint which package was likely the culprit. Some of you might ask, why are we not using Poetry for this task? Well, frankly, our solution predates the popularity of Poetry, and it works so well, so we never had a need. And there's another reason, because there are some things that are outside the scope of Poetry that can break your workflow. So not only pip dependencies matter. Now you have updated your Docker file, you can check that no pip dependency changed, but your output has changed. How is that possible? So another possible issue is some of the systems library changed of the Docker. So when you're running precise calculations, change in application can break the results even without changing your pip dependencies. So one of such example is if, for example, BLAS library gets updated, it can change the floating points very slightly, and that adds up, and you can have few pixels slightly different. So we need to be able to also detect that. So then you did everything right. You see what dependency changed. Everything seemed correct. So, but some user starts to complain that something breaks afterwards. So how do you avoid that? We don't have a silver bullet for that. It's just updating dependencies will always carry the risk that something may break. Only way to mitigate that is to have good unit test coverage and good integration test coverage that alerts you when that happens. Now I will quickly touch parallelism. So the goal is very simple. We want to run analysis fast, and we want to run over big areas. So first the rule, anything that can go wrong will go wrong. especially when you're running hundreds of pods that process tasks. Something will eventually fail, either the client side or server side, so transient network timeouts, bad reads, faulty hardware, you name it, it's gonna fail. So we don't want a single fail task to cause the whole workflow to fail. One of the steps we use to mitigate that is we employ a simple library called retrying in Python. It's a simple but powerful tool. You can simply define when to retry, how many times, with which delay. You can also let it retry only on selected failures. So this way you can mitigate temporary failures. There's another issue. So you have implemented retrying and things briefly work well. But however, one day users keep hitting the same error again and again. Sometimes the issue occurs only after some expensive process is done. And if you keep retrying it, you are wasting your resources for nothing. And in this case, in our case, mostly it's caused if our satellite data provider brings us, let's say, corrupted metadata in small part of the image. So to solve that, we use so-called error sentinels. So specific failed tasks can save error sentinels to database or storage, so that whole workflow can be quickly stopped without having to reprocess again. And there is another issue. So how do you avoid running the same tasks twice? Your code is running, platform is stable, but two users run the same analysis at the same time. How do you avoid collisions? How do you avoid running the same thing twice? This, I think, is a complicated problem. I think it's worthy of presentation on its own. But what we do is we use Redis, which is in-memory database for you who don't know it, to lock the chain of tasks. We call these locked tasks critical sections. And every time critical section gets started, it tries to write down to Redis. If it succeeds, it's not in Redis yet, and it executes. And if it's already in Redis, it just waits until it can run, and then itself, it becomes locked. There is a lot of thought behind it, so if the locked or task already processed, it can then skip and just go right to the next task. This brings me to our final part, which is resource scaling. This is something that we need to do to be as effective as possible with our compute resources. In the case of big requested analysis, we need to scale up fast to analyze requests. Afterwards, we need to scale down so we are not paying for unused resources. However, at any time, our platform needs to be responsive, at least with some minimal resource available. So the main problem in this is compute costs money. Each virtual machine provisioned from node pool, in our case, gets built. And running 500 virtual machines at the same time gets expensive fast. So we like to keep our costs down. And to do that, we are not running a constant amount of pods ready at all times. Or on contrary, we are running bare necessities, as I mentioned. And those resources that are running, we want them to be running as utilized as possible. So that brings me to the question, how do you scale up and down? Usually in Kubernetes, they offer horizontal scaling, where they allow you to increase amount of pods based on your defined metrics. So by default, Kubernetes allows you to scale an amount of pods based on CPU utilization. However, as I mentioned, In the ideal case, we would like to have our services running fully utilized, and having pods to run at 100% CPU doesn't necessarily mean that we need to scale another pod. To do that, we are scaling number of pods directly from Python code. And in the shown example, we are scaling it to 10 replicas for the selected pod. So now you can scale up and down directly, but how to decide whether to increase or decrease? So we have a special service. In Python, it's called autoscaler. And we use the number of tasks waiting in the queue to decide how many pods we want to scale. When we see there are zero tasks in the queue, we can totally scale pods to 0. Where there are a lot of tasks, we increase it. So, well, now you can scale up and down, which is great. However, imagine that you received a huge task. So let's say we have 10,000 tasks waiting in the queue, and each task takes approximately 20 seconds to process. We don't really want to have, let's say, 5,000 pods running immediately, as was shown in the previous simple implementation, because of various reasons. Some of them is like startup of pods takes some time, getting resources from your cloud providers takes some time, you pay while the pod is being scaled up. So, or while it's starting, sorry about. So what would happen is you would try to scale it to 5,000, and by the time everything is scaled up properly, you would probably have to scale it down again because the queue would be empty. So this is very inefficient. Solving this properly is also a very hard task. What we did at the beginning, and we still do, is we have a custom class as a PID controller that is scaling our platform up and down. So it keeps the previous state, so how many pods we had before, how many tasks do we have in queue, and tries to smooth out this kind of bumps. So, and then we can tune the controller or the class to make the scaling as fast as possible without going too high, and or too fast or too slow. So this is also, I think, worth another whole presentation. And this brings me to my final slide. Thank you for your attention. And if you find it interesting and are willing to solve some hard, challenging problems, then we are hiring. Thank you.
Thank you, Jakub. We have time for a few questions. This one is interesting. What are you using for DAG orchestration?
Second.
What are you using for direct data cyclic graph orchestration?
Yes, we are using just some library. I think it's called Network X in Python, and that works well for us. It's pretty powerful for this use case.
How do you receive the source imagery data, and where do you store it?
Yeah, so that differs from provider to provider. Some providers will provide you with APIs, which you download. Some providers just like have the, let's say, FTP sources, and sometimes you just download it from S3 buckets. So it varies, and what we do, we also save it in S3 bucket after we process it. So that way, it's pretty fast.